Hey there, welcome back. Tonight we're going to talk about some math stuff that sounds really confusing but actually makes more sense when you break it down. This is going to be nice and slow, no rush, just exploring some weird and interesting things about numbers and geometry that might seem scary at first, but are actually pretty cool once you understand them. So let's just ease into this. You're comfortable, right? Good. Because we're about to spend some time with concepts that have been messing with people's heads for centuries. And the thing is, these ideas aren't actually that complicated when you strip away all the fancy language and just think about what's really going on. Let's start with something that probably bothered you in school at some point: division by zero. You remember your teacher saying you can't divide by zero, right? And maybe you thought, why not? What's the big deal? It's just zero. Well, here's the thing. Division is really just asking a question. When you divide one number by another, you're asking how many times the bottom number fits into the top number. Makes sense. But what happens when you ask how many times 0 fits into any number? Think about that for a second. You're trying to add up zeros until you reach that number. 0 plus 0 plus 0. You could do that forever. You'd never get there. There's no answer. It's like asking how many empty boxes you need to fill a room. The question itself doesn't really work. And here's where it gets weirder. What about 0 divided by 0? Now you might think, well, that should just be 1, right? Because any number divided by itself is 1. But hold on. Remember, division is asking how many times the bottom number fits into the top number. So 0 divided by 0 is asking how many zeros do you need to add together to get 0. Well, that could be 1 0, or it could be any amount of zeros, because 0 plus 0 always equals 0. So the answer could be anything. That's why mathematicians just say it's undefined. Not that it equals infinity or anything like that, just that the question itself is broken. Think about it like this. Imagine you have a pizza and you want to divide it among 0 people. How much pizza does each person get? The question is nonsense because there are no people. You can't distribute something to nobody. The operation just doesn't make sense in that context. Now, what's interesting is that you can get close to dividing by 0. Like, if you divide some number by 1, you get that same number. If you divide by a half, you get double. If you divide by a tenth, you get 10 times as much. The smaller the number you divide by, the bigger the answer gets. So as you get closer and closer to dividing by 0, the answer gets bigger and bigger, heading toward infinity. But you never actually get there. It's like walking toward the horizon. You can walk forever, but you'll never reach it. This connects to something else that's pretty mind-bending: infinity itself. Now, infinity isn't really a number, it's more like an idea. It represents something that goes on forever, never ending. And when you start thinking about infinity, some really strange stuff happens. There's this thing called the Hilbert Hotel paradox. Imagine a hotel with infinite rooms. Room 1, room 2, room 3, and so on, forever. Now imagine every single room is occupied. Someone's staying in every room. The hotel is completely full. Then a new guest shows up. In a normal hotel, you'd say, sorry, we're full. But in an infinite hotel, you can still make room. How? You ask the person in room 1 to move to room 2. The person in room 2 moves to room 3. The person in room 3 moves to room 4. Everyone shifts down one room. Since there are infinite rooms, everyone still has a place to stay. And now, room 1 is empty for the new guest. That's already pretty weird, right? But it gets stranger. What if an infinite number of new guests show up? An entire bus of infinite people arrives at your infinite hotel that's already completely full. Can you accommodate them? Turns out, yes. You ask everyone to move to double their current room number. Now all the odd-numbered rooms are empty. That's infinite empty rooms. So you have space for your infinite new guests. This is so weird because it breaks our normal understanding of what full means. In the world of infinity, full doesn't mean you can't add more. You can always make room. This is because infinity plus 1 is still infinity. Infinity plus infinity is still infinity. Infinity divided by 2 is still infinity. These aren't normal numbers that follow normal rules. Here's another thing about infinity that messes with people. There are actually different sizes of infinity. I know that sounds crazy. How can infinity be bigger than infinity? But it's true. The infinity of counting numbers, going on forever, that's one size of infinity. The infinity of all numbers between 0 and 1, including every possible decimal, that's a bigger infinity. How do we know? Well, imagine trying to make a complete list of all the counting numbers. You could keep going forever, but in theory, you could list them all in order. Every counting number would eventually show up on your list. Now try to list all the decimal numbers between 0 and 1. Between any two decimals, there are infinite other decimals. You could never make a complete list. There's no way to count them all. This infinity is bigger. It's uncountable. A mathematician named Cantor proved this in a really clever way. He showed that even if you tried to make a list of all the decimal numbers, you could always construct a new number that wasn't on your list. So the set of all decimals is larger than the set of counting numbers, even though both are infinite. Mind-blowing stuff. But let's shift gears a bit. Let's talk about imaginary numbers. Now, these have a terrible name because it makes them sound fake, like they don't exist. But they're just as real as any other number. They're called imaginary for historical reasons, basically because when they were first discovered, mathematicians thought they were weird and impossible. Here's the deal. You know that when you multiply two positive numbers, you get a positive number, and when you multiply two negative numbers, you also get a positive number. Negative times negative equals positive. So what number, when you multiply it by itself, gives you a negative number? There isn't one. Not in the regular numbers we're used to. So mathematicians invented a new number. They called it I, and they said that I times I equals -1. This little invention opened up a whole new world of mathematics. With I, you can take the square root of any negative number. These are called imaginary numbers. Now, you might think, okay, but what's the point? Why do we need these weird numbers? Well, it turns out they're incredibly useful. Engineers use them all the time to analyze electrical circuits. Physicists use them in quantum mechanics. They show up in signal processing, which is how your phone compresses audio and video. Pretty much any wave-like phenomenon can be described more easily using imaginary numbers. And here's what's cool. Imaginary numbers aren't just some abstract mathematical trick. They represent something real, which is rotation. When you multiply by I, you're rotating by 90 degrees in a special kind of number plane. The regular numbers we know sit on a horizontal line. Imaginary numbers sit on a vertical line. Together, they form a plane where you can describe any rotation or combination of movements. It's like having coordinates, but for numbers themselves. Think about it like this. If you're walking east and someone asks you to turn 90 degrees, you're now walking north. That's like multiplying by I. If you turn 90 degrees again, you're walking west, which is the opposite of east. That's like multiplying by I again, which gives you -1. Turn 90 degrees more times, and you're back where you started. The rotation completes a full circle, so imaginary numbers aren't imaginary at all. They're just numbers that describe a different dimension, perpendicular to the regular number line we're used to. They expand our understanding of what numbers can be. Alright, let's talk about something even stranger. There's this thing called the Banach-Tarski paradox, and it might be one of the weirdest things in all of mathematics. Here's what it says. You can take a solid ball, like a sphere, cut it into a few pieces, and rearrange those pieces to make two complete spheres, each the exact same size as the original. You haven't added anything. You haven't stretched anything. You just moved the pieces around, and now you have two balls instead of one. This sounds completely impossible, right? Like magic. How can you double something just by cutting it up and rearranging it? The trick is that the pieces you cut aren't normal pieces. They're not like slicing a pizza. These pieces are infinitely complex, infinitely jagged, made up of scattered points that don't have a measurable volume. They exist in the abstract world of mathematics, where you can have sets of points that are so weird and scattered that normal rules about volume don't apply. The paradox uses something called the axiom of choice, which is a rule in mathematics that says if you have a bunch of sets, even infinitely many sets, you can choose one element from each set. This seems pretty harmless, but it leads to some bizarre consequences, like the Banach-Tarski paradox. Now, this doesn't work in real life. You can't actually cut up a gold ball and turn it into 2 gold balls. Matter isn't infinitely divisible. Atoms exist, quantum mechanics exists, but in the pure mathematical world, where we're just talking about sets of points in space, you really can do this. It's not a trick or a flaw in mathematics. It's just showing us that infinity is genuinely weird, and our intuitions about how things should work break down when we're dealing with infinite sets. Some mathematicians hate this paradox. They think it shows that the axiom of choice leads to nonsense. Others love it. They think it reveals deep truths about the nature of infinity and shows how rich and strange mathematics can be. It's been debated for almost a century now, and people still don't agree on what it means. But here's what I find fascinating about it. The Banach-Tarski paradox uses a technique similar to the Hilbert Hotel. Remember how we could fit infinite new guests into an already full infinite hotel? The paradox does something similar with the points on a sphere. It shifts them around in clever ways, using rotations to create copies of itself. It's like the sphere version of moving hotel guests between rooms. You're not creating new points, you're just reorganizing the ones you have in a way that seems impossible but mathematically works out. Let's slow down for a second here and think about what connects all these ideas. Division by zero, infinity, imaginary numbers, the Banach-Tarski paradox. They're all about pushing our understanding of numbers to their limits. They're all about what happens when you take familiar concepts and extend them into unfamiliar territory. Math in school often feels like following rules. Memorize formulas, solve for x. But real mathematics is about exploring ideas, asking what if, seeing what happens when you try something that seems impossible. What if we tried to divide by zero? What if there were infinite hotel rooms? What if we invented a number whose square is negative? What if we could cut a sphere into pieces and rearrange them? And sometimes, when you explore these questions, you find answers that don't make intuitive sense. They reveal that the mathematical universe is bigger and stranger than we thought. Let's talk about another infinity problem that's been puzzling people for thousands of years. It's called Zeno's paradox. The ancient Greek philosopher Zeno came up with this one. Imagine you want to walk across a room. Before you can get all the way across, you have to get halfway across, right? And before you can get halfway across, you have to get a quarter of the way across. And before that, an eighth of the way, and so on, dividing the distance in half forever. So in theory, you have to complete infinite tasks before you can cross the room. You have to reach each fractional point along the way, and this goes on forever. How can you ever complete infinite tasks? Yet, obviously, people cross rooms all the time. We do it without thinking. So what's going on? The answer has to do with understanding infinity better. Yes, there are infinite steps, but those steps take less and less time. The first half of the room might take you a certain amount of time to cross. The next quarter takes half that time. The next eighth takes half again. The times keep getting smaller, and when you add them all up, even though there are infinitely many of them, they add up to a finite total. After a finite amount of time, you've completed all infinite tasks and crossed the room. This was really hard for ancient philosophers to understand because they didn't have a good mathematical framework for dealing with infinity. But now we do. We have calculus. We have the concept of limits. We understand that infinite sums can have finite totals. The distance gets divided infinitely, but time also gets divided infinitely, and everything works out. What's beautiful about Zeno's paradox is that it forced mathematicians to think more carefully about infinity. It seemed like a proof that motion was impossible. but instead, it led to deeper understanding. It helped us develop better tools for thinking about continuous change, about how things can be infinitely divisible yet still coherent. Here's another quick one that plays with infinity. There's this series where you alternate adding and subtracting 1 minus 1 plus 1 minus 1 plus 1 minus 1, going on forever. What does it equal? Well, if you group it one way, each pair sums to 0, so the answer is 0. But if you group it differently, you get a different result. The series doesn't actually settle on a single value. It's another case where infinity breaks our normal rules. Mathematicians had to develop careful rules about when you can rearrange the terms in an infinite series and when you can't. For series that behave nicely, you can. For series that don't, like this one, rearranging can give you different answers, which means the series itself isn't well behaved. Now let's talk about something that seems simple, but turns out to be surprisingly deep: zero itself. We take zero for granted now, but for most of human history, people didn't have a concept of zero as a number. The ancient Greeks didn't use zero. The Romans didn't have it. How can you represent nothing with something? Zero came from India, probably around the 7th century. It was a revolutionary idea. It allowed for place value systems, where the position of a digit matters. Without zero, you couldn't distinguish between different magnitudes of numbers easily. Zero makes our entire number system work. But zero is weird. It's the only number that when you add it to something, nothing changes. It's the only number that when you multiply by it, everything becomes zero. It's neither positive nor negative. It sits right at the boundary between the two. Zero also plays a key role in calculus. When you're finding the slope of a curve at a point, you're essentially dealing with quantities approaching zero. But you do it in a clever way, using limits, so you get a meaningful answer. Calculus is full of these moments where you're working with quantities that approach zero without ever quite reaching it. There's also the question of whether zero is a natural number or not. Mathematicians don't all agree. Some say the natural numbers start at 1 because those are the counting numbers and you don't count starting from 0. Others say natural numbers include 0 because it's a whole number and it's useful to include it. It depends on context and what you're trying to do. Let's think about another concept that confuses people: the idea of irrational numbers. These are numbers that can't be written as a fraction, pi, right? It goes on forever without repeating. You can't write pi as one whole number divided by another whole number. It's irrational. The ancient Greeks discovered that the square root of 2 was irrational, and it kind of freaked them out. They believed everything could be expressed as ratios of whole numbers. That was the foundation of their mathematical worldview. But the square root of 2 ruins that. If you have a square where each side is 1 unit long, the diagonal is the square root of 2 units long. And that's an irrational number. You can't express it exactly as a fraction. The proof that the square root of 2 is irrational is pretty elegant. You assume it can be written as a fraction in simplest form. Then you show that both the top and bottom would have to be even numbers. But if both are even, the fraction isn't in simplest form. Contradiction. So it can't be written as a fraction at all. What's wild is that there are way more irrational numbers than rational numbers. We talked about different sizes of infinity earlier. The set of rational numbers, all the fractions, is countably infinite. You could theoretically list them all, but the set of irrational numbers is uncountably infinite. It's a bigger infinity. So in some sense, almost all numbers are irrational. The rational numbers are just a tiny sliver of all the numbers out there. Pi is irrational, but it's also something more special. It's transcendental, which means it's not the solution to any polynomial equation with whole number coefficients. Most numbers are transcendental, actually, but proving a specific number is transcendental is really hard. Pi and e are both transcendental. This means they're not just irrational, they're somehow even more disconnected from the regular counting numbers. Alright, here's something that sounds complicated but is actually kind of beautiful when you see what it means. Complex numbers. We talked about imaginary numbers earlier, like I, the square root of -1. Complex numbers are what you get when you combine regular numbers with imaginary numbers. They have a real part and an imaginary part together. You can add, subtract, multiply, and divide complex numbers just like regular numbers, and they have this beautiful geometric interpretation. Every complex number corresponds to a point on a plane. The real part tells you how far left or right to go. The imaginary part tells you how far up or down to go. It's like coordinates on a map. This means you can think of complex numbers as vectors, as arrows pointing from the origin to a specific point. And when you multiply complex numbers, you're doing two things at once. You're changing the length of the vector and you're rotating it. It's like a combination of scaling and spinning. This makes complex numbers incredibly useful for describing anything that involves rotation or oscillation, which is a lot of physics and engineering. There's this amazing formula called Euler's formula. It connects exponential functions with trigonometry using complex numbers. It looks complicated at first, but what it's saying is that exponential growth, when you involve imaginary numbers, becomes circular motion. Growth and rotation are connected through complex numbers. And there's a special case that connects e, I, and pi with 1 and 0. This equation is beautiful because it ties together some of the most important constants in mathematics. Complex numbers also solve problems that regular numbers can't. Remember how we said you can't take the square root of a negative number using regular numbers? With complex numbers, you can. Every polynomial equation has a solution in the complex numbers. This is called the fundamental theorem of algebra. It means that complex numbers complete the number system in a really satisfying way. There are no more gaps, no more unsolvable equations. Everything works out. Now, let's talk about what happens when you try to extend numbers even further. Mathematicians have created things called quaternions, which are like complex numbers but with more imaginary dimensions. Quaternions are used in computer graphics and game development because they're really good at describing rotations in space without running into certain technical problems. There are also octonions, which extend this even further. But here's the thing. As you keep extending the number system, you lose properties. Regular numbers have all the nice properties. Addition and multiplication work the way you'd expect. Complex numbers lose one property. You can't say one complex number is bigger or smaller than another in a meaningful way. Quaternions lose commutativity. The order you multiply them in matters. Octonions lose even more structure. So there's a trade-off. You get more dimensions, more expressiveness, but you lose some of the nice clean rules. Let's think about another weird thing. There's this concept in mathematics called a fractal. Fractals are shapes that look the same at every scale. You can zoom in forever and you keep seeing the same pattern. The classic example is the Mandelbrot set, this incredibly intricate pattern that you can zoom into infinitely and it never stops being detailed. But here's what's weird about fractals. They have fractional dimension. We usually think of dimension as a whole number. A line is one-dimensional. A square is two-dimensional. There's a cube is three-dimensional. But some fractals are somewhere in between. They're more than one-dimensional but less than two-dimensional. It sounds impossible, but it makes sense when you think about how much space the fractal fills. A curve that's really jagged and fills a lot of area might have a dimension higher than 1 but lower than 2. The most famous example is the coastline paradox. If you try to measure the coastline of a country, the answer depends on how detailed you get. If you measure with a long ruler, you get one answer. If you measure with a shorter ruler, capturing more of the little ins and outs, you get a longer answer. As you use smaller and smaller rulers, the measured length keeps increasing. In a mathematical sense, coastlines have infinite length. Their fractal dimension is higher than 1. They're more crinkly than a smooth curve. Fractals show up all over nature. Trees branch in fractal patterns. Rivers and their tributaries form fractals. Clouds, mountains, snowflakes all have fractal structure. Nature seems to love these self-similar, infinitely detailed patterns, and mathematically, They're generated by really simple rules repeated over and over. You don't need complicated equations. Just take a simple shape, apply a transformation, repeat, do it infinitely many times, and you get these stunningly complex patterns. Here's another thing that messes with people's intuition: the Monty Hall problem. It's a probability puzzle. Imagine you're on a game show. There are 3 doors. Behind one door is a car. Behind the other 2 are goats. You pick a door, let's say door 1. The host, who knows what's behind each door, opens another door, let's say door 3, revealing a goat. Now the host asks you if you want to stick with door 1 or switch to door 2. Most people think it doesn't matter. There are 2 doors left, so it's 50-50, right? But actually, you should always switch. If you switch, you have a 2/3 chance of winning the car. If you stay, you only have a 1/3 chance. This seems totally wrong at first. How can switching improve your odds? Here's why it works. When you first picked door 1, you had a 1/3 chance of being right. That means there's a 2/3 chance the car is behind one of the other 2 doors. When the host opens door 3 and shows a goat, that doesn't change the fact that there's a 2/3 chance the car is behind one of the other doors. But now you know it's not behind door 3. So all that probability is concentrated on door 2. By switching, you're taking advantage of that. Another way to think about it is, imagine there were 100 doors instead of 3. You pick one. The host opens 98 other doors, all showing goats, leaving your original pick and one other door. Do you switch? Of course you do. Your first pick had a 1 in 100 chance of being right. The other door has essentially all the remaining probability. It's the same logic with 3 doors, just less obvious. This problem famously stumped a lot of smart people, including mathematicians. When it was first published, people wrote angry letters saying the solution was wrong. It's a great example of how probability can be counterintuitive. Let's talk about another probability thing: the birthday paradox. In a room with just a small number of people, there's a better than even chance that 2 of them share a birthday. This seems impossible at first. There are so many possible birthdays. How can you get a match with so few people? The key is, you're not looking for a specific birthday, you're looking for any match between any 2 people. With even a modest number of people, there are many possible pairs. Each pair has a small chance of sharing a birthday, but when you add up all those chances, it gets surprisingly high, surprisingly fast. You can work it out the other way too. What's the probability that no 2 people share a birthday? The first person can have any birthday. The second person has to have a different birthday. The third person has to avoid both of those birthdays. Multiply these probabilities together and you see how quickly they drop. Before long, it becomes more likely than not that at least 2 people share a birthday. This is one of those things where your intuition misleads you because you're thinking about it wrong. You're thinking about your own birthday and how unlikely it is that someone else shares it. But the problem is asking about any pair of people sharing any birthday, which is a much broader question. Alright, here's something else that's kind of trippy: Gödel's incompleteness theorems. These are results about the limits of mathematical proof. Kurt Gödel proved that in any mathematical system that's complex enough to do basic arithmetic, there will always be true statements that can't be proven within that system. No matter how many rules you set up, there will always be things that are true but unprovable. This is huge. It means mathematics is inherently incomplete. You can't have a perfect set of rules that proves everything. There will always be gaps, always be questions that can't be answered using the tools you have. You might think you could just add more rules to cover the gaps, but Gödel showed that won't work. The new expanded system will have its own unprovable truths. It's like a mathematical version of the liar's paradox. If I say this statement is false, is it true or false? If it's true, then it's false. If it's false, then it's true. There's no consistent way to assign it a truth value. Gödel created a mathematical statement that essentially says this statement cannot be proven. If it can be proven, then it's false, which means you've proven something false, so your system is inconsistent. If it can't be proven, then it's true, which means there's a true statement that can't be proven, so your system is incomplete. This shook the foundations of mathematics when Gödel published it. Mathematicians had hoped to find a complete and consistent set of axioms that could prove all mathematical truths. Gödel showed that's impossible. There will always be truths beyond the reach of any particular formal system. But here's the thing, and this is important. Just because something can't be proven in a particular system doesn't mean it's not true. It just means you need a broader perspective to see it. You might need to step outside the system, add new axioms, think in a bigger framework. Mathematics is always expanding, always reaching for new tools to tackle the problems that the old tools couldn't handle. Let's think about dimensions again for a minute. We live in 3 spatial dimensions. You can move left, right, forward, backward, up, down. Those are the 3 dimensions of space. We also experience time, which is sometimes called the 4th dimension. But mathematicians work with any number of dimensions. 4-dimensional space, 5-dimensional space, 100-dimensional space. These aren't physical places. You can't visit them. But mathematically, they make perfect sense. In 4-dimensional space, you can have a hypercube, which is like a cube but extended into a 4th perpendicular direction. It's impossible to visualize properly because we're stuck in 3 dimensions, but you can understand it mathematically. It has more vertices, more edges, more faces than a regular cube. Every time you add a dimension, the structure gets more complex. There's this thing called a tesseract, which is a 4-dimensional cube. You can project it into 3 dimensions, kind of like how you can draw a cube on a flat piece of paper. The projection is distorted, but it gives you an idea of the structure. Looking at a projection of a tesseract is wild because it looks impossible, like an optical illusion, but it's actually a perfectly reasonable object in 4 dimensions. Higher dimensions are used all the time in mathematics and physics. String theory requires 10 or 11 dimensions depending on the version. Most of those extra dimensions are supposedly curled up, so small we can't perceive them. But mathematically, they're necessary to make the theory work. Whether that reflects physical reality or is just a mathematical artifact, we don't know yet. Machine learning also uses high-dimensional spaces. When you're training a neural network to recognize images, you're essentially working in a space with thousands or millions of dimensions, one for each pixel or feature. The algorithms find patterns and structures in those high-dimensional spaces that would be impossible to visualize but are perfectly well-defined mathematically. Here's another fun thing about dimensions. In high-dimensional spaces, most of the volume of a sphere is near the surface, not in the center. This is really counterintuitive. In 3 dimensions, a sphere has a lot of volume in the middle, but as you go to higher dimensions, the volume gets pushed outward. By the time you're in a really high-dimensional space, almost all the volume is in a thin shell near the surface. The center is essentially empty. This has practical consequences. It's one reason why high-dimensional data analysis is hard. Most of the space is empty, and the data points tend to cluster near the edges of the space. It's called the curse of dimensionality. Techniques that work well in 2 or 3 dimensions often fail in high dimensions because the geometry is just different. Let's talk about something called the pigeonhole principle. It's super simple but surprisingly powerful. The principle says if you have more objects than containers and you want to put all the objects in containers, at least one container must hold more than one object. Obvious, right? But you can use this to prove some cool stuff. For example, in any group of people that's larger than the number of days in a year, at least 2 of them must share a birthday. Why? Because there are only so many possible birthdays. More people than birthdays means some birthdays must be shared. By the pigeonhole principle, here's a weirder one. In any group of 6 people, either 3 of them are all mutual friends, or 3 of them are all mutual strangers. This sounds like a guess, but you can prove it with the pigeonhole principle and a bit of clever thinking. It's part of a branch of mathematics called Ramsey theory, which is all about finding order in chaos, showing that certain patterns must emerge even in seemingly random situations. Or, here's another example. Take any points inside a square, at least two of them are within a certain distance of each other. You can prove this by dividing the square into smaller squares. More points than squares means some squares must contain multiple points, and points in the same small square can't be too far apart. The pigeonhole principle seems trivial, but it's a workhorse in mathematics. It shows up all over the place in proofs. Sometimes the hardest part is figuring out what the objects are and what the containers are. Now let's think about something called the coastline problem we touched on earlier, but in more detail. Benoit Mandelbrot, the guy who really popularized fractals, asked this question: how long is the coast of Britain? And the answer is, it depends on how you measure it. If you use a long measuring stick, you'll get one answer, but the coast has bays and inlets and peninsulas. If you use a shorter measuring stick, you'll capture more of those details and get a longer measurement. Use an even shorter stick, and you'll measure around individual rocks. Use a microscopic stick, and you're measuring around grains of sand, around individual atoms. The finer your measurement, the longer the coast becomes. In the limit, as your measuring stick approaches zero length, the coast's length approaches infinity. This is true of any natural, irregular coastline. It doesn't have a well-defined length in the traditional sense. The measured length depends on the scale of measurement. This is what Mandelbrot meant when he said coastlines have a fractal dimension. They're more crinkly than a smooth curve. This has practical implications. If two countries dispute the length of their shared border, they might genuinely get different answers depending on how they measure. There's no single correct answer. You have to specify the scale of measurement to get a meaningful result. The same thing applies to other natural phenomena. How long is a river? How big is the surface area of a sponge? How much border does a cloud have? All these questions have fractal answers. The more closely you look, the more detail you see, and the measurements keep growing. Alright, let's ease into something a bit more abstract. There's this concept in mathematics called a set. A set is just a collection of things. Could be numbers, could be shapes, could be anything. The things in the set are called elements. Pretty simple. But when you start thinking about sets of sets, things get weird. Can a set contain itself? Like, imagine the set of all sets. Does that set contain itself? It must, right? Because it's a set and it contains all sets. But this leads to paradoxes. There's this thing called Russell's paradox. Consider the set of all sets that do not contain themselves. Does this set contain itself? If it does, then by definition it shouldn't, because it only contains sets that don't contain themselves. But if it doesn't contain itself, then by definition it should, because it's a set that doesn't contain itself. Contradiction either way. This paradox showed that you have to be careful about how you define sets. You can't just say any collection of things is a set. You need rules. Modern set theory has axioms that prevent these paradoxes. Basically, you're not allowed to form certain kinds of sets. Like the set of all sets. It's not that they exist and we can't talk about them. They're not well-defined objects in the mathematical framework we use. This might seem like abstract nitpicking, but it matters. Set theory is the foundation of mathematics. All of math can be built up from sets if you're careful about it. Numbers are defined as sets. Functions are defined as sets. Everything rests on this foundation, so making sure the foundation is consistent and paradox-free is crucial. Let's talk about something called the continuum hypothesis. Remember we said there are different sizes of infinity? The infinity of counting numbers is the smallest infinity. The infinity of all real numbers is larger. It's called the cardinality of the continuum. The continuum hypothesis asks whether there's an infinity between these two. Is there a set that's bigger than the counting numbers, but smaller than the real numbers? For a long time, people didn't know. It seemed like there shouldn't be, but nobody could prove it. Then in the 1960s, Paul Cohen proved something shocking. The continuum hypothesis is independent of the standard axioms of set theory. That means you can't prove it true or false using the usual rules. You can add it as an extra axiom and get a consistent system, or you can add its negation as an axiom and get a different consistent system. Both are equally valid mathematically. This was mind-blowing. It means there are questions in mathematics that don't have a definite answer within the standard framework. The answer depends on what axioms you choose to work with. It's like geometry. You can work with flat Euclidean geometry, or you can work with curved, non-Euclidean geometry. Both are consistent. Which one you use depends on what you're trying to describe. So there are these unresolved questions sitting at the heart of mathematics. Not because we haven't been clever enough to solve them, but because they're genuinely beyond the reach of our current framework. We might develop new axioms, new ways of thinking that make the answers clear, or we might decide that the question itself doesn't have a single answer. Let me tell you about another paradox, a bit lighter, the unexpected hanging paradox. A judge tells a prisoner that they'll be hanged at noon on one of the next several days, but the day will be a surprise. The prisoner won't know which day until the executioner arrives that morning. The prisoner thinks about this and reasons as follows. I can't be hanged on the last day because if I'm still alive the evening before, I'll know the hanging must be the next day, so it won't be a surprise. So the last day is ruled out. But if the last day is ruled out, I can't be hanged on the second to last day either, because if I'm still alive the evening before that, I'll know it must be that day, since the last day is impossible. But then the executioner comes on some middle day, and the prisoner is genuinely surprised. The hanging happens exactly as the judge said. What went wrong with the prisoner's reasoning? This paradox has been debated for decades. Different philosophers and logicians give different explanations. The issue seems to be that the prisoner's reasoning involves self-reference and assumptions about their own knowledge in a tricky way. The conclusion that they can't be hanged is incompatible with the premise that they will be hanged, so something in the chain of reasoning must be flawed. But pinpointing exactly where is surprisingly hard. It's a great example of how logic can tie itself in knots when you start reasoning about your own reasoning. It's related to things like Gödel's theorems and the liar's paradox. Self-reference is a powerful tool in mathematics and logic, but it's also a source of weirdness and paradox. Alright, let's talk about prime numbers for a bit. Prime numbers are numbers that are only divisible by 1 and themselves. They're the building blocks of all numbers, because every number can be written as a product of primes in exactly one way. The primes are like atoms of arithmetic, but the distribution of primes is mysterious. There's no simple formula that generates all the primes. They seem almost random, appearing at irregular intervals as you go up the number line. But they're not truly random. There are patterns, deep patterns, but they're hard to describe and harder to prove. One pattern is that primes become less frequent as numbers get larger. This makes sense because larger numbers have more potential divisors, but they never stop appearing. There are infinitely many primes. Euclid proved this over 2,000 years ago with a beautiful argument. Suppose there were only finitely many primes, multiply them all together and add 1. This new number isn't divisible by any of the primes on your list, because dividing it by any of them leaves a remainder of 1. So either this new number is prime itself, or it's divisible by a prime not on your list. Either way, your list wasn't complete. Contradiction, so there must be infinitely many primes. There are still unsolved problems about primes that have stumped mathematicians for centuries. The twin prime conjecture says there are infinitely many pairs of primes that differ by 2. We strongly believe this is true, but nobody has proved it. The Goldbach conjecture says every even number greater than 2 can be written as the sum of 2 primes. Computers have checked this for enormous numbers, and it always works, but there's no proof that it works for all numbers. Primes are also connected to one of the most famous unsolved problems in mathematics, the Riemann hypothesis. This is a conjecture about the distribution of primes, relating them to a complex function. If the Riemann hypothesis is true, it would tell us a lot about how primes are spaced out. People have been trying to prove it for over 150 years. There's $1 million prize for solving it. It's one of the great mysteries of mathematics. What's cool is that primes have practical applications too. Modern cryptography relies on the fact that multiplying two large primes is easy, but factoring a large number back into its prime factors is really hard. Your credit card information is protected by this asymmetry. If someone figures out a fast way to factor large numbers, a lot of encryption would become useless overnight. Let's shift to talking about limits for a moment. This is a concept from calculus that's really important. A limit is what a function approaches as the input approaches some value. Think about a function where as the input gets bigger and bigger, the output gets closer and closer to some number. That number is the limit. Limits let you handle situations where you can't just plug in a number directly, like what happens to a function at a point where it's not defined. If you look at what happens as you approach that point from either side, you can often figure out what the function should be there, even though it technically isn't defined. The limit exists, even though the function value doesn't. This is how calculus deals with instantaneous rates of change. The derivative of a function at a point is the limit of the average rate of change as the interval gets smaller and smaller. You're taking the slope of a line, connecting 2 points, and letting those points get closer and closer together until they're essentially the same point. The line becomes tangent to the curve. Without limits, calculus wouldn't work. Limits also let you work with infinite series. We talked about adding up infinitely many terms earlier. The sum of an infinite series is defined as the limit of the partial sums. You add up the first term, then the first 2 terms, then the first 3 terms, and so on. If this sequence of partial sums approaches a finite number, that's the sum of the series. If it doesn't, the series diverges and doesn't have a sum. For example, adding up powers of 1/2 forever gives you 2. Each partial sum gets a bit bigger, but it never exceeds 2. It approaches exactly 2, so the infinite sum equals 2. But adding up the reciprocals of whole numbers diverges. The partial sums grow without bound, slowly but steadily. There's no finite limit. Understanding limits deeply is key to understanding calculus, which is key to understanding pretty much all of modern science and engineering. Physics, chemistry, economics, biology, all rely on calculus, and calculus relies on limits. Here's something else about infinity that's trippy. There's a function that's continuous everywhere but differentiable nowhere. That means the graph of the function has no breaks or jumps, but at no point does it have a well-defined slope. It's infinitely jagged, fractal-like, crinkly at every scale. You can zoom in anywhere, and it still looks rough and irregular. This seems impossible at first. How can a function be smooth enough to be continuous but rough enough to have no slope anywhere? But it exists. It was constructed specifically to be a counterexample to an earlier conjecture. You can have a continuous function that's nowhere differentiable. Reality is stranger than our intuitions suggest. This function is built by adding up infinitely many wave patterns with increasing frequencies and decreasing heights. Each individual wave is smooth, but when you add infinitely many of them in just the right way, the sum becomes this bizarre, nowhere differentiable thing. It's a beautiful example of how infinity can create structures that don't exist in any finite context. Now let's talk about something called the axiom of choice again, because it leads to some wild stuff. The axiom of choice says that if you have a collection of non-empty sets, you can choose one element from each set, even if there are infinitely many sets and you don't have a rule for making the choices. This sounds harmless, but it leads to the Banach-Tarski paradox we talked about earlier. It also leads to other weird things, like non-measurable sets. These are sets that don't have a well-defined size or volume. You can't assign them a measure in any consistent way. They're too pathological, too spread out, and weird. Most mathematicians accept the axiom of choice because it makes a lot of things easier. Without it, you lose some powerful theorems. But there are mathematicians who reject it, who work in frameworks where the axiom of choice doesn't hold. In those frameworks, you don't get the Banach-Tarski paradox, and all sets are measurable, but you also lose some convenient tools. It's a trade-off. You can't have everything. If you want the axiom of choice, you get powerful theorems, but also strange paradoxes. If you don't want the paradoxes, you have to give up some of the theorems. There's no free lunch. Let me tell you about a concept called cardinality matching in a different way. Think about the idea that two sets have the same size if you can pair up their elements one to one. The set of fingers on your left hand and the set of fingers on your right hand have the same size because you can match them up perfectly. This works for infinite sets too. The set of all counting numbers and the set of all even numbers have the same size, even though it seems like there should be half as many even numbers. But you can pair them up perfectly. Every counting number gets matched with an even number, and every even number gets matched with a counting number. So they have the same cardinality, the same size of infinity. But the set of all counting numbers and the set of all real numbers between 0 and 1 don't have the same size. There's no way to pair them up completely. Cantor proved this with his diagonal argument. Suppose you tried to list all the real numbers between 0 and 1. Cantor showed you could construct a new number not on your list. You can always find a number that's missing. So you can't list all the real numbers. They're a bigger infinity. This was revolutionary. It showed that not all infinities are the same size. It opened up a whole new world of mathematics, studying the arithmetic of different sizes of infinity. Cantor's work was controversial at the time. Some mathematicians rejected it, but it's now a cornerstone of modern mathematics. Alright, here's something fun. There's a problem called the Collatz conjecture. Pick any positive whole number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Take the result and repeat the process. Do this over and over. The conjecture is that no matter what number you start with, you'll eventually reach 1. And once you reach 1, the sequence loops. 1 becomes 4, 4 becomes 2, 2 becomes 1, and so on forever. Try it with any number you want. It goes up and down, all over the place, but eventually it reaches 1. People have checked this for enormous numbers. It always works. But nobody has proved that it works for all numbers. There might be some number out there that goes off to infinity or loops in some other way. Or there might be a proof that every number eventually reaches 1, but we haven't found it yet. This is a great example of a problem that's easy to state, easy to play with, but apparently really hard to solve. Mathematicians have made progress on related questions, but the main conjecture remains open. It's humbling. Mathematics is full of questions that look simple but turn out to be incredibly deep. Let's talk about topology for a bit. Topology is sometimes called rubber sheet geometry. It's about properties of shapes that don't change when you stretch or bend or twist them, as long as you don't tear or glue. So a coffee cup and a donut are the same in topology because you can deform one into the other. They both have one hole. But a ball and a donut are different because a ball has no holes and a donut has one hole. You can't deform one into the other without tearing. The number of holes is a topological property. Topology asks weird questions, like, can you turn a sphere inside out smoothly, without creasing or tearing, passing the surface through itself? Turns out, yes. There's a sequence of transformations that does it. It's hard to visualize, but it works. You can watch animations of it online, and it's mesmerizing. Another topological puzzle is the Mobius strip. Take a strip of paper, give it a half twist, and tape the ends together. Now you have a surface with only one side and one edge. If you start drawing a line down the middle of the strip, you'll come back to where you started without ever lifting your pen, and you'll have drawn on both sides of the strip because there's only one side. If you cut a Mobius strip down the middle lengthwise, you don't get two separate loops. You get one longer loop with more twists. Cut that one down the middle, and you get two interlocking loops. It's wild. The topology of the Mobius strip makes it behave in unexpected ways. Topology has practical applications too. Network theory, data analysis, even understanding the shape of the universe, all use topological ideas. It's about understanding structure in a very abstract, flexible way. Here's a famous topology problem that was only solved recently, the Poincare conjecture. It asks whether every simply connected, closed, three-dimensional shape is topologically the same as a three-dimensional sphere. A simply connected shape is one where any loop can be shrunk down to a point without leaving the shape. The surface of a ball is simply connected. The surface of a donut is not, because a loop going around the hole can't be shrunk to a point. For two-dimensional surfaces, the answer was known for a long time. Yes, every simply connected closed surface is a sphere, but in 3 dimensions, it was an open question for 100 years. Then, a mathematician named Perelman proved it. He used techniques from different areas of math, studying how shapes evolve over time under certain flows. His proof was a massive achievement. He was offered $1 million prize for solving it. He turned it down. He didn't want the recognition or the money. He just wanted to do math. The Poincare conjecture and its proof opened up new techniques and new questions. It's an example of how solving one problem often leads to a cascade of new insights. Alright, let's ease back to something a bit more concrete. Think about symmetry. Symmetry is when something looks the same after you transform it in some way. A square has rotational symmetry. If you rotate it 90 degrees, it looks the same. It also has reflectional symmetry. If you flip it along certain lines, it looks the same. The study of symmetry is called group theory. A group is a set of transformations that you can combine and reverse. Like, the symmetries of a square form a group. You can rotate, then reflect, and that's equivalent to some other symmetry. You can undo any symmetry by doing the opposite transformation. Group theory is incredibly powerful. It's used in particle physics to classify particles. It's used in chemistry to understand molecular structure. It's used in cryptography and coding theory. The idea of symmetry and group structure appears everywhere. There's this thing called the monster group, which is the largest sporadic simple group. Simple groups are the building blocks of all finite groups, kind of like how primes are the building blocks of numbers. Most simple groups fall into infinite families. But there are a couple dozen sporadic groups that don't fit into any family. They're weird exceptions, and the monster is the biggest and weirdest of them all. The monster group is unimaginably huge. It's connected to strange areas of mathematics and even to string theory. There are hints that the monster is connected to deep structures in physics, but we don't fully understand the connections yet. It's one of the mysteries at the frontier of mathematics. Let me tell you about a different kind of infinity problem. There's this series where you add up the reciprocals of all positive counting numbers, 1 plus 1/2 plus 1/3 plus 1/4, and so on. Does this series converge to a finite value, or does it grow without bound? It grows without bound. It diverges. Even though each term gets smaller and smaller, approaching zero, the sum keeps growing, slowly but surely, toward infinity. This is surprising at first because the terms shrink so fast. But there are always more terms, and they're always adding something, so the total keeps climbing. You can see this by grouping terms cleverly. Each group you create adds up to at least a certain amount, so the total exceeds that amount repeated infinitely many times. That's infinity. But if you change the series slightly, it can converge. The sum of 1 over each counting number squared does converge. It approaches a finite value. The difference is subtle, but it makes all the difference in whether the series converges or diverges. These kinds of distinctions are important in calculus and analysis. Understanding which series converge and which don't, and what they converge to, is a major area of study. It has applications everywhere. You're adding up infinite contributions to get a total. Alright, let's talk about chaos theory for a moment. Chaos theory studies systems that are very sensitive to initial conditions. A tiny change at the start can lead to huge differences later on. This is popularly known as the butterfly effect. A butterfly flapping its wings could theoretically set off a chain of events that leads to a tornado somewhere else. The classic example is the weather. Weather is a chaotic system. You can make predictions for a few days out, but beyond that, small uncertainties in the current conditions grow exponentially and your predictions become useless. This isn't because we don't have good models or powerful computers. It's because the system itself is unpredictable beyond a certain time horizon. Chaos appears in lots of places. Population dynamics, the orbits of asteroids, the dripping of a faucet, the beating of a heart. These systems can look random, but they're actually deterministic. The future is completely determined by the present, but because of sensitivity to initial conditions, predicting the future is practically impossible. One of the key concepts in chaos theory is the strange attractor. This is a set of states that a chaotic system tends to evolve toward, but the motion within that set is erratic and unpredictable. The system never settles into a steady pattern, but it also never escapes the attractor. It loops and swirls in a complex, never-repeating dance. Chaos theory changed how we think about determinism and predictability. Just because a system follows fixed rules doesn't mean we can predict its behavior. There are limits to what we can know, even in a perfectly deterministic universe. Let's think about game theory now. Game theory is the study of strategic decision-making, where the outcome depends on the choices of multiple players. The classic example is the prisoner's dilemma. Two people are arrested and interrogated separately. Each is given a choice: betray the other or stay silent. The payoffs depend on what both people choose. From each player's perspective, betraying is the better move, no matter what the other person does. So both players betray, and both get a worse outcome than if they'd both stayed silent. This is called a Nash equilibrium, where no player can improve their outcome by changing their strategy alone. It's not the best outcome for both players together, but it's stable. Neither player has an incentive to change unilaterally. The prisoner's dilemma shows up in all kinds of real-world situations: arms races, price competition, environmental issues. Each individual has an incentive to defect, but if everyone defects, everyone is worse off than if everyone had cooperated. Game theory helps us understand these dynamics and think about mechanisms that might encourage cooperation. There are also games where cooperation can emerge. If you play repeatedly, certain strategies can do well. Start by cooperating, then do whatever the other player did last time. This rewards cooperation and punishes betrayal, and it can lead to stable cooperation over time. The evolution of cooperation is a fascinating area of study. Okay, let's think about something called the Sleeping Beauty problem. This is a probability puzzle that philosophers and mathematicians argue about. Here's the setup. Sleeping Beauty volunteers for an experiment. She's put to sleep. A fair coin is tossed. If it's heads, she's woken once and interviewed. If it's tails, she's woken twice, interviewed each time, with her memory erased between wakings. Whenever she's woken, she doesn't know which waking it is. When she's woken and interviewed, she's asked, "What's your credence that the coin came up heads?" What should she answer? One argument says 1/2. The coin is fair, so the probability of heads is 1/2, and she has no new information to change that. Another argument says 1/3. There are 3 possible situations from her perspective, all equally likely. In only one of those is the coin heads, so her credence should be 1/3. People have written tons of papers arguing for each side. It depends on how you think about probability and what information you consider relevant. It's a great example of how probability can be subtle and context-dependent. Let me tell you about one more thing before we wrap up. There's this concept called a P-adic number. Normal numbers are based on powers of 10, but you can define numbers based on powers of a prime. These are called P-adic numbers. In P-adic numbers, size works differently. A number is small if it's divisible by high powers of the prime. The more factors of the prime a number has, the smaller it is in the P-adic sense. This is backwards from normal intuition, but it's consistent and useful. P-adic numbers are used in number theory and algebraic geometry. They give a different perspective on problems, sometimes making things easier to see or prove. They're another example of how mathematics extends beyond the familiar, creating new structures that obey their own internal logic. So we've covered a lot tonight: division by zero, infinity and paradoxes, imaginary and complex numbers, dimensions, fractals, probability puzzles, chaos, game theory, and weird number systems. All these ideas are connected by a common theme. Mathematics is about exploring the boundaries of what's possible, questioning our assumptions, and discovering structures that go beyond everyday intuition. Math isn't just about getting the right answer on a test. It's about curiosity, about asking what if, about building frameworks that help us understand patterns and relationships. Some of these ideas might seem abstract, but they've led to real applications, from cryptography to computer graphics to understanding the laws of physics. And a lot of math is still unknown. There are unsolved problems, open conjectures, mysteries waiting to be explored. The Riemann hypothesis, the Collatz conjecture, the continuum hypothesis, and many more. Mathematics is a living, growing field, constantly evolving as people ask new questions and develop new tools. The beautiful thing is that math is accessible to anyone willing to think carefully and ask questions. You don't need expensive equipment or special resources, just curiosity and persistence. The ideas we've talked about tonight were all discovered by people asking simple questions and following the logic wherever it led, even when it led to surprising or counterintuitive places. But we're not quite done yet. Let me tell you about a few more things that are worth thinking about as you drift off. There's this concept called the four-color theorem. It says that any map, no matter how complicated, can be colored using just 4 colors so that no two regions sharing a border have the same color. This seems simple enough that you'd think someone would have proved it a long time ago. But it wasn't proved until the 1970s, and the proof was controversial because it relied on a computer checking thousands of cases. It was one of the first major theorems proved with computer assistance. Some mathematicians were uncomfortable with this because they couldn't verify the proof by hand, but the theorem is now widely accepted. What's interesting is that the four-color theorem is easy to state and seems like it should be easy to prove, but it's not. Lots of attempted proofs were published over the years, and all of them had errors. The actual proof is complicated and involves careful case analysis. It's a reminder that sometimes simple questions have complex answers. There's a related question about coloring maps on other surfaces. On a sphere, which is basically the same as a flat map, you need 4 colors. On a torus, you need more. On shapes with more holes, you need even more colors. As the surface gets more complicated, you need more colors. There's actually a formula that tells you how many colors you need based on the number of holes. It's beautiful how topology and combinatorics connect. Let me tell you about Euler's formula for polyhedra. A polyhedron is a 3-dimensional shape made of flat faces. Euler discovered that for any convex polyhedron, if you count the vertices, edges, and faces in a certain way, you always get the same result. The number of vertices minus the number of edges plus the number of faces always equals 2. This formula is remarkable because it connects the geometry of the shape to a simple number, and it generalizes. For polyhedra with holes in them, the formula changes. The number you get, called the Euler characteristic, tells you about the topology of the shape. It's an invariant, something that doesn't change even if you deform the shape. It's a deep connection between different areas of mathematics. Euler's formula extends to graphs and networks too. If you draw a graph on a plane without any edges crossing, the formula still holds, with faces being the regions the graph divides the plane into. This has applications in computer science, network design, and many other fields. Let's talk about something called the halting problem. This is from computer science, but it's deeply mathematical. The halting problem asks whether a given computer program will eventually stop or run forever. Alan Turing proved that there's no general algorithm that can solve the halting problem for all possible programs. No matter how clever you are, you can't write a program that correctly determines whether any other program will halt or run forever. It's impossible in principle. The proof is beautiful. Suppose you had such a program. You could construct a new program that uses it and does the opposite of what the analysis predicts. If the analysis says a program halts, make it run forever. If the analysis says it runs forever, make it halt. Then run this new program on itself. You get a contradiction either way. So, no such program can exist. This is similar to Gödel's incompleteness theorems. Self-reference creates situations where no consistent answer is possible. The halting problem shows that there are limits to what computers can do, limits that no amount of engineering can overcome. Some questions are undecidable. Here's another classic problem, the traveling salesman problem. You have a list of cities and the distances between each pair. You want to find the shortest route that visits each city exactly once and returns to the start. Sounds simple, right? But as the number of cities grows, the number of possible routes explodes. Checking every route to find the shortest one becomes impossible. The traveling salesman problem is no problem hard. That means there's no known efficient algorithm that can solve it in general. The best known algorithms take impractically long for large numbers of cities. But we also don't know that no efficient algorithm exists. It's possible someone will discover a clever trick someday. The question of whether every problem whose solution can be quickly verified can also be quickly solved is one of the biggest open problems in computer science and mathematics. In practice, people use approximation algorithms and heuristics to find good routes, even if they're not guaranteed to be the absolute shortest. These methods work well enough for practical purposes. Let's think about voting paradoxes for a moment. You'd think that if everyone votes fairly, you'd get a reasonable outcome. But Arrow's impossibility theorem shows that there's no perfect voting system. Arrow's theorem says that if you have 3 or more options to choose from, any voting system that tries to combine everyone's preferences will either be dictatorial or will violate some other reasonable sounding criteria. Different voting systems make different trade-offs. There's no perfect system that satisfies all the criteria we'd like. This is troubling. It means that democracy, at least in terms of combining preferences into a collective choice, has limitations. Different voting systems make different compromises. There's no perfect system. This connects to game theory and social choice theory. How do we make decisions as a group? How do we balance individual preferences with collective outcomes? These aren't just mathematical questions. They have real implications for politics, economics, and society. Let me tell you about the law of large numbers. This is a theorem in probability that says if you repeat an experiment many times, the average of the results will get closer and closer to the expected value. Like, if you flip a fair coin many times, the proportion of heads will approach 1/2. This seems obvious, but it's important to understand what it's saying and what it's not saying. It doesn't say that if you get more heads than tails early on, you're due for more tails to balance things out. Each coin flip is independent. The probability of heads is always 1/2, no matter what happened before. The law of large numbers says that over many flips, the proportion evens out, not because of any balancing force, but just because rare events become less influential as the sample size grows. The gambler's fallacy is when people think past results affect future probabilities in independent events. But each event is independent. The probability is the same every time. Understanding the law of large numbers and avoiding the gambler's fallacy is important in statistics, decision-making, and everyday reasoning. It helps you think clearly about risk and uncertainty. There's a related concept called regression to the mean. If you measure something that has randomness, extreme values are more likely to be followed by values closer to the average. This gets misinterpreted a lot. People see regression to the mean and think there's some force pulling things toward average, but it's just a statistical artifact of randomness. Recognizing this helps you avoid overinterpreting fluctuations. Let me talk about the Drake equation for a moment. This isn't pure math, but it's a fascinating use of mathematics to think about big questions. The Drake equation estimates the number of communicative extraterrestrial civilizations in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, and so on. The problem is that most of these factors are highly uncertain. Multiply together several uncertain factors, and the final answer can range over many orders of magnitude. The Drake equation isn't meant to give a precise answer. It's a framework for thinking about the question. It breaks down a complex problem into components and shows what we need to know to answer it. This kind of mathematical modeling is useful even when the numbers are uncertain. Speaking of modeling, let's think about the logistic map. This is a simple equation used to model population growth. Next year's population depends on this year's population times a growth rate times 1 minus the current population relative to carrying capacity. It's a simple feedback loop, but depending on the growth rate, the logistic map can exhibit incredibly complex behavior. For some values, the population settles to a steady state. For others, it oscillates. For still others, it becomes chaotic, jumping unpredictably. This was a revelation. A simple equation with no randomness can produce chaos. The logistic map is now a textbook example of how complexity can emerge from simplicity. The bifurcation diagram of the logistic map is stunning. It shows a tree-like structure with branching and self-similar patterns. It's fractal. The same patterns repeat at different scales. It's a visual representation of the transition from order to chaos. Let's think about knot theory. A knot, in mathematics, is a closed loop in space that's tangled up. The simplest knot is a loop with no crossings. Then there are more complicated knots with crossings. Two knots are considered the same if you can deform one into the other without cutting. The question is, how do you tell if two knots are the same or different? This is harder than it sounds. Mathematicians have developed invariants, quantities you can calculate for a knot that don't change under deformation. If two knots have different invariants, they're definitely different knots. Knot theory has surprising applications. DNA molecules can get knotted. Proteins fold in complex ways. Understanding knots mathematically helps us understand these biological processes. There's also a connection to physics. In quantum field theory, certain particle interactions can be described using knot diagrams. Knots appear in string theory. What started as abstract curiosity turns out to connect to the physical world. Let me tell you about the Monty Hall problem in more detail. After the host opens a door revealing a goat, why does switching give you better odds? When you first picked a door, you had a 1/3 chance of picking the car. The host knows where the car is and always opens a door with a goat, so the host is giving you information. If the car was behind one of the other two doors, which it is most of the time, the host has shown you which one it's not behind. By switching, you're choosing the door that has better odds. Another way to see it is, imagine 100 doors. You pick one. The host opens many doors, all with goats, leaving your original door and one other. Do you switch? Of course. Your original pick had low odds. The other door has much higher odds. Same logic with 3 doors, just less obvious. The Monty Hall problem is a great lesson in conditional probability. The host's action of opening a door changes the probabilities because the host's choice is not random. That information is valuable, and switching lets you use it. Let's talk about the Street Petersburg paradox. Imagine a game where a coin is flipped repeatedly until it comes up tails. The payout doubles each flip. Tails on the first flip wins a small amount. Tails on the second flip wins double. On the third flip, quadruple, and so on. What's a fair price to pay to play this game? The expected value is infinite, so the calculation suggests the game is worth any amount, but intuitively, no one would pay much to play. The resolution involves understanding that expected value isn't the only consideration. risk aversion, and practical limits matter. The paradox shows that naive expected value calculations don't always match rational decision-making. It led to the development of expected utility theory. Here's something about irrational numbers and normal numbers. A normal number is one where every digit appears equally often in the long run. Pi is suspected to be normal, but we haven't proved it. Almost all real numbers are normal, but proving a specific number is normal is very hard. If pi is normal, that means every possible finite sequence of digits appears somewhere in its decimal expansion. Your phone number is in there, everything. This is true of any normal number. It contains all finite information. But containing all finite information doesn't mean the number encodes anything useful. You can't use pi as a compression algorithm because finding a particular sequence requires searching through potentially huge amounts of digits. The information is there, but it's not accessible. There's a concept called Kolmogorov complexity, which measures the complexity of a string by the length of the shortest computer program that can produce it. A random string has high complexity. A pattern string has low complexity. Pi has very low Kolmogorov complexity, even though its digits look random. You can write a short program that computes as many digits of pi as you want. The pattern is in the mathematical structure, not in the digits themselves. Let me tell you about tessellations. A tessellation is a way of covering a surface with shapes that fit together perfectly. Squares tessellate. A tessellation in the Leven en een Bayerham, a facials were namen and moral. Hexagons tessellate. Lots of shapes tessellate. But some shapes don't tessellate on their own. Regular pentagons don't tile the plane. There are always gaps or overlaps. But you can combine different shapes to create interesting tessellations. There's also the question of aperiodic tessellations, tilings that cover the plane but never repeat exactly. Roger Penrose discovered a set of two tile shapes that only tessellate aperiodically. You can cover the whole plane with them, but the pattern never repeats. Penrose tilings have a kind of long-range order without being periodic. They're related to quasicrystals, a state of matter that has ordered structure without periodicity. The connection between abstract mathematical tilings and physical materials is beautiful. Recently, a single shape was discovered that tiles the plane aperiodically. It can tile the plane, but only in ways that never repeat. This was a major breakthrough. Let's talk about the Riemann zeta function a bit more. This function has deep connections to prime numbers. The zeros of the function, the values where it equals 0, have a deep connection to the distribution of primes. The Riemann hypothesis conjectures that all the important zeros lie on a specific line in the complex plane. If the Riemann hypothesis is true, it would give us precise information about how primes are distributed. It would confirm conjectures about gaps between primes and much more. It's one of the most important unsolved problems in mathematics. Thousands of mathematicians have worked on it. Computers have verified it for many zeros. But a proof remains elusive. Some think the proof will require entirely new mathematical techniques. It's a monument to how much we still don't know. Let me tell you about the concept of mathematical proof itself. A proof is a logical argument that shows a statement must be true based on accepted axioms and previously proven results. It's not about convincing someone emotionally or showing examples. It's about rigorous deduction. There are different styles of proof. Direct proof, where you start with the assumptions and derive the conclusion. Proof by contradiction, where you assume the opposite and show that leads to absurdity. Proof by induction, where you prove a base case and then show the pattern continues. Some proofs are short and elegant. Other proofs are hundreds of pages long, requiring deep technical machinery. There's a tension in mathematics between finding proofs and understanding why things are true. A proof establishes truth, but it might not give insight. Sometimes you can prove something without really understanding the underlying reason. Other times, a proof is so illuminating that it changes how you think about the entire subject. Let's think about continued fractions. These are a way of representing numbers as a sequence. Every real number can be written as an integer plus 1 divided by another integer plus 1 divided by another integer, and so on. For rational numbers, the process terminates. For irrational numbers, it goes on forever. Continued fractions are useful for approximation. If you truncate the continued fraction at some point, you get a rational approximation. And continued fractions give the best possible rational approximations in a precise sense. The golden ratio has a particularly simple continued fraction, just ones all the way down. This reflects the golden ratio's self-similar properties. Continued fractions reveal patterns and relationships that aren't obvious in decimal form. They're another perspective on numbers. Okay, let's think about mathematical notation for a moment. The symbols we use aren't inherent to mathematics. They're conventions that developed over time. Different cultures and time periods use different symbols. But notation matters. Good notation makes thinking easier. When Leibniz invented his notation for calculus, it made calculus more intuitive and easier to work with. Ideas that were hard to express became clearer. Mathematical notation is a kind of language, and like any language, it shapes how we think. When you see a complex equation written in clear notation, the structure becomes visible. You can see relationships and patterns. There's an art to choosing good notation. It should be concise, but not cryptic. It should suggest the meaning when possible. It should extend naturally to related concepts. Let me tell you about the continuum again, but from a different angle. The real numbers form a continuum, an unbroken line without gaps. Between any two real numbers, there's another real number. In fact, there are infinitely many. You can zoom in forever and always find more numbers. But the rationals, despite being dense in the reals, have gaps. The irrationals fill those gaps. The reals combine rationals and irrationals into a complete number system where every sequence that should converge does converge. This completeness property is crucial for calculus. Without it, limits might not exist, series might not converge, and all the machinery of analysis would break down. The continuum is the foundation on which much of modern mathematics rests. There's also a philosophical question about whether real numbers are real. We can never specify most real numbers explicitly. Most reals are unnameable. They exist in the mathematical framework, but they're not accessible individually. Does that mean they're just useful fictions? Mathematicians generally don't worry too much about this. The real numbers work, they're consistent, they're useful. Whether they're real in some metaphysical sense is a question for philosophers, but it's an interesting question nonetheless. Let's talk about optimization. Many problems involve finding the best solution among many possibilities, the shortest path, the largest profit, the most efficient design. Calculus provides tools for optimization. If you want to maximize or minimize a function, you find where the derivative is 0. Those are the critical points. Then you check which critical points are actually maxima or minima. But not all optimization problems are smooth and differentiable. Some involve discrete choices or constraints. Some optimization problems are very hard. We don't know any efficient algorithm to solve them. In practice, people use heuristics and approximation algorithms. These are techniques for finding good solutions, even when finding the optimal solution is intractable. They're used in machine learning, operations research, engineering design, and countless other fields. Let me tell you about the hairy ball theorem. This is a result in topology with a memorable name. It says you can't comb a hairy ball flat. More precisely, if you have a sphere covered in hair and you try to comb all the hairs flat against the surface, there must be at least one point where the hair sticks up or creates a whorl. Mathematically, this is a statement about vector fields on a sphere. You can't have a continuous, nowhere zero tangent vector field on a sphere. This has a practical consequence. Weather on Earth is modeled as a vector field on a sphere. The hairy ball theorem implies there must always be at least one point where the wind isn't blowing, like the eye of a storm. The hairy ball theorem doesn't apply to all surfaces. On a torus, you can have a non-zero vector field everywhere. you can comb a hairy donut flat. The theorem depends on the topology of the surface. Let's think about symmetry in art and nature. Snowflakes have six-fold rotational symmetry. Flowers often have radial symmetry. Butterfly wings have bilateral symmetry. These symmetries arise from underlying physical or biological processes. Mathematics gives us a language to describe and classify these symmetries. Group theory is the study of symmetry. Different symmetry groups correspond to different patterns. In art, artists have explored symmetry for millennia. Islamic geometric patterns use complex symmetries. Escher created tessellations with figures that fit together perfectly. Understanding the mathematics of symmetry allows artists to create new patterns. There's also broken symmetry in physics. Sometimes a system has a symmetry mathematically, but the actual state of the system doesn't. This concept is important in particle physics and cosmology. Okay, let's talk about infinity one more time. There's a concept called an ordinal number, which extends the idea of ordering to infinite sets. The first infinite ordinal represents the ordering of the natural numbers. After all, the natural numbers comes another ordinal, then another, and so on, climbing higher and higher into the transfinite. Ordinals are different from cardinals. Cardinals measure size, ordinals measure order. Different ordinals can have the same cardinality but different structures. Working with transfinite ordinals and cardinals is like exploring a landscape of infinities. It's abstract and can feel far removed from everyday math, but it's a rich and beautiful area of study. Cantor, who pioneered this work, faced criticism from some of his contemporaries. Some mathematicians thought infinity was a topic for theology, not mathematics. But Cantor persisted, and his work is now a cornerstone of set theory. Alright, we're getting near the end here. Let me just touch on a few more ideas. There's the concept of a mathematical structure. A structure is a set together with some operations or relations. Studying structures abstractly is a powerful approach. It lets you prove things once, in general, that apply to many specific examples. This is the essence of abstract algebra. There's also the idea of isomorphism, which is when two structures are the same in every important way, even if they're described differently. Recognizing isomorphisms lets you transfer knowledge from one context to another. Finally, let's think about mathematical beauty. Mathematicians talk about elegant proofs, beautiful theorems, surprising connections. What makes mathematics beautiful? It's not just about getting the right answer. It's about simplicity, symmetry, unexpectedness, depth. A beautiful proof is one that reveals why something is true in a clear, economical way. A beautiful theorem connects disparate areas or reveals a hidden pattern. It changes how you see the subject. Mathematics is an art as much as a science. It's creative, intuitive, aesthetic. The best mathematics has a quality of inevitability, like discovering something that was always there. And that's where I'll leave things tonight. We've wandered through so many topics: infinity, zero, imaginary numbers, paradoxes, proofs, symmetry, chaos, topology, knots, primes, and so much more. These ideas are all part of the vast landscape of mathematics, a landscape that's still being explored every day. Whether you're drifting off to sleep or wide awake with your mind buzzing, I hope you found something here that sparked your curiosity or gave you a new way of thinking about numbers and patterns. Mathematics is full of surprises, full of beauty, full of deep truths, and it's accessible to anyone willing to ask questions and think carefully. Thanks for spending this time with me. Sleep well. Actually, let me tell you about a few more things before you drift off completely. There's so much more to explore in the world of mathematics, and we've only scratched the surface. Let's talk about something called the birthday problem in more depth. We touched on it earlier, but there's more to think about here. The counterintuitive nature of this problem really shows how our brains aren't naturally wired for probability. When you think about birthdays, you're probably thinking about your own birthday. You know how rare it is to meet someone who shares your exact birthday. It doesn't happen that often. So when someone says that in a relatively small group, there's a good chance of finding a match, it sounds wrong. But the key insight is that we're not looking for someone who matches your specific birthday. We're looking for any two people in the room who match each other. That's a completely different question. Every pair of people in the room is a potential match, and with even a modest number of people, you have a lot of potential pairs. Think about it geometrically. If you have people in a room, the number of possible pairs grows much faster than the number of people. It's not a linear relationship, it's quadratic. So even though each individual pair has a small chance of matching, when you have many pairs, the cumulative probability adds up quickly. This same kind of reasoning appears in other contexts too. Cryptography, for instance, worries about what's called the birthday attack. If you're trying to find two inputs that produce the same output from a hash function, you don't need to try nearly as many inputs as you might think. The birthday problem logic applies, and collisions show up sooner than expected. Let's shift to thinking about something called the axiom of choice again, but from yet another angle. The axiom of choice seems so innocuous. All it says is that if you have a bunch of boxes, each containing at least one thing, you can reach into each box and pick out one item. That's it. How could that lead to paradoxes? The problem comes when you have infinitely many boxes. In the finite case, there's no issue. You can physically demonstrate the choice. But with infinitely many boxes, especially when there's no rule or pattern for what to choose, the axiom of choice asserts that such a selection is still possible, even though you can't actually describe or perform it. This bothers some mathematicians because it feels like asserting the existence of something you can't construct or specify. It's like saying there's a number with certain properties but refusing to tell anyone what that number is. The axiom of choice says these selections exist without giving you any way to find them. And yet, accepting the axiom of choice unlocks so much mathematics. So many theorems depend on it. Without it, whole branches of mathematics become much more limited and awkward. So most mathematicians accept it, paradoxes and all, because the alternative is worse. There's an interesting middle ground that some mathematicians explore. They work in frameworks where you can use the axiom of choice for countable collections but not uncountable ones, or where you can use it in some contexts but not others. These compromise positions try to get the benefits while avoiding the worst paradoxes. It's an ongoing area of research in mathematical logic. Let me tell you about something called the continuum hypothesis again, but with more context. When Cantor discovered that there are different sizes of infinity, he naturally wondered whether there are any infinities between the counting numbers and the real numbers. The counting numbers are the smallest infinite set. The real numbers are provably larger. But is there something in between? A set that's bigger than the counting numbers but smaller than the reals? Cantor believed the answer was no. He thought the reals are the next size up, with nothing in between. This is the continuum hypothesis. But despite working on it for years, Cantor couldn't prove it. Other mathematicians tried too. It became one of the famous unsolved problems. Then, in the mid-20th century, Gödel and Cohen between them showed something shocking. The continuum hypothesis can neither be proved nor disproved from the standard axioms of set theory. It's independent. What does that mean? It means that mathematics, as currently formulated, doesn't have enough information to answer the question. You can add the continuum hypothesis as a new axiom, and everything stays consistent. Or you can add its negation as an axiom, and that's also consistent. Both versions of mathematics are equally valid. This was disturbing to many mathematicians. It suggests that some fundamental questions don't have answers, at least not without adding new axioms. And which axioms should we add? There's no objective way to decide. It's a matter of preference, of which mathematics you find more useful or more elegant. Some mathematicians have proposed new axioms that would settle the continuum hypothesis. These large cardinal axioms assert the existence of certain very large infinities with special properties. With these axioms, you can prove the continuum hypothesis false, but not everyone accepts these new axioms. It remains controversial. The whole situation is philosophically fascinating. It shows that mathematics isn't completely fixed and determined. There are choices to be made, and different choices lead to different mathematics. Let's think about perfect numbers for a bit. A perfect number is a number that equals the sum of its proper divisors. The divisors of a number, not including the number itself, add up to the number. The smallest example is 6. Its divisors are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. So 6 is perfect. The next perfect number is much larger. Then the next is larger still. Perfect numbers are rare. Only a handful are known. And all the known perfect numbers have a special form. They're all even, and they all follow a specific pattern related to prime numbers. Euclid discovered a formula for generating even perfect numbers over 2,000 years ago. If you take a certain kind of prime number, you can use it to construct a perfect number. And every even perfect number comes from this formula. It's a beautiful connection between perfect numbers and primes. But here's the mystery. Are there any odd perfect numbers? Nobody knows. None have ever been found, despite extensive computer searches. If an odd perfect number exists, it's huge. It has to have many prime factors. It has to satisfy various conditions, but we can't prove that no odd perfect number exists. This is another example of a simple question that's apparently incredibly hard to answer. Perfect numbers seem like a curiosity, a recreational topic, but they connect to deep questions in number theory. Whether odd perfect numbers exist remains one of the unsolved problems. Let me tell you about something called the harmonic series again, but think about it in terms of music. The harmonic series in music is the sequence of overtones that resonate when you play a note. When you pluck a string, it vibrates at a fundamental frequency, but it also vibrates at twice that frequency, 3 times, 4 times, and so on. The mathematical harmonic series is named after this because it's the sum of the reciprocals of the counting numbers 1 plus 1/2 plus 1/3 plus 1/4, and so on. Each term is the reciprocal of the next counting number, just as each harmonic frequency is a multiple of the fundamental. We said earlier that the harmonic series diverges. It grows without bound, even though each term gets smaller. This is counterintuitive but important. It means that even though you're adding tinier and tinier amounts, the sum still eventually exceeds any finite value you name. There's a famous proof attributed to Nicole Oresme, a medieval philosopher, showing that the harmonic series diverges. He grouped the terms cleverly to show that the sum exceeds 1/2 repeatedly, infinitely many times. Each group contributes more than 1/2 to the total, so the sum is infinite. This has practical implications. If you stack blocks on top of each other, each one hanging over the edge of the one below, how far can you make the top block overhang the bottom? With enough blocks, you can make the overhang as large as you want. It grows like the harmonic series. So it's unbounded. In theory, with infinitely many blocks, the top block could be arbitrarily far from the bottom. In practice, friction and stability limit you, but mathematically, the harmonic series tells you it's possible. Let's talk about something called the Cantor set. This is a fractal with bizarre properties. You start with a line segment, remove the middle third, leaving 2 segments. Then remove the middle third of each of those segments, leaving 4 segments. Keep doing this forever. What's left? The Cantor set. It's an infinite collection of points, but it has total length 0. All the removed middle thirds add up to the entire original length. Yet, infinitely many points remain. It's uncountably infinite, the same size as the real numbers, but it has no length. The Cantor set is nowhere dense. It has no intervals. It's all gaps with scattered points. Yet it's perfect, meaning every point is a limit of other points in the set. It's closed and uncountable, but has measure 0. It's a counterintuitive object that violates many of our intuitions about sets and size. The Cantor set shows up in various areas of mathematics. It's a standard example in topology and measure theory. It's used to construct pathological functions and counterexamples. Despite seeming like an abstract curiosity, it's actually quite important. There's also a connection to base 3 representation. If you write numbers in base 3, using only the digits 0, 1, and 2, the Cantor set consists of all numbers in the interval from 0 to 1, whose base 3 expansion uses only 0s and 2s. No 1s. This gives you another way to think about the structure of the Cantor set. Let me tell you about something called the Fibonacci sequence. This is one of the most famous sequences in mathematics. You start with 0 and 1, then each subsequent term is the sum of the previous 2 terms. So you get 0, 1, 1, 2, 3, 5, 8, and so on. Each number is the sum of the 2 before it. The Fibonacci sequence shows up everywhere in nature. The spirals in pine cones and sunflowers follow Fibonacci numbers. The branching of trees often follows the pattern. Flower petals frequently come in Fibonacci numbers. It's uncanny how often nature seems to use this sequence. There's also a connection to the golden ratio. If you take the ratio of successive Fibonacci numbers, like dividing one term by the previous term, the ratios approach the golden ratio. The further you go in the sequence, the closer the ratio gets. In the limit, it's exactly the golden ratio. The golden ratio itself is a special number. It's the number such that if you divide a line segment into 2 parts in this ratio, the ratio of the whole to the longer part equals the ratio of the longer part to the shorter part. It's approximately 1.618, and it has all sorts of interesting properties. The golden ratio shows up in art and architecture. The Parthenon, paintings by Leonardo da Vinci, the proportions of the human body all supposedly incorporate the golden ratio. Whether these are intentional design choices or coincidences is debated, but the golden ratio definitely has an aesthetic appeal that people have recognized for centuries. Mathematically, the golden ratio is interesting because it's the most irrational number in a specific sense. It's the hardest number to approximate with rational fractions. Its continued fraction expansion is all ones, which means its rational approximations converge as slowly as possible. This makes it optimal for certain purposes, like the spacing of leaves around a stem to maximize sunlight exposure. Nature seems to have discovered this optimization. Let's think about something called modular arithmetic. This is arithmetic where numbers wrap around after reaching a certain value, like a clock. On a clock, if it's 10 o'clock and you add 5 hours, you get 3 o'clock, not 15 o'clock. The numbers wrap around at 12. Modular arithmetic generalizes this. You pick a modulus, like 12 for clock arithmetic, then you do arithmetic as usual, but whenever you reach the modulus, you wrap back to 0. So, in arithmetic modulo 12, 10 plus 5 equals 3. This might seem like a quirky variant of normal arithmetic, but it's incredibly useful. Modular arithmetic is used in cryptography, computer science, and number theory. Many properties of numbers are easier to study using modular arithmetic. For example, checking whether a large number is divisible by 9 is easy using modular arithmetic. A number is divisible by 9 if and only if the sum of its digits is divisible by 9. This is because in arithmetic modulo 9, the powers of 10 all equal 1. So a number and the sum of its digits are equivalent modulo 9. Fermat's little theorem, a cornerstone of number theory, is a statement about modular arithmetic. It says that if you take any number, raise it to the power of a prime, and subtract the number, the result is divisible by that prime. This theorem is used in primality testing and cryptography. The RSA encryption algorithm, which secures much of the internet, relies on modular arithmetic and properties of primes. The security comes from the fact that multiplying 2 large primes is easy, but factoring the product back into primes is hard. Modular arithmetic makes the encryption and decryption work. Let me tell you about something called the twin prime conjecture. We talked about primes being the building blocks of numbers. Twin primes are pairs of primes that differ by 2, like 3 and 5, or 11 and 13, or 29 and 31. Twin primes seem to keep appearing as you go up the number line, but they get rarer. The gaps between primes generally get larger as numbers get bigger, yet twin primes keep showing up, at least as far as we've checked. The twin prime conjecture says there are infinitely many twin primes. They never stop appearing, even though they become sparse. We believe this is true. The evidence is overwhelming, but nobody has proved it. Recently, there's been progress. Mathematicians have proved that there are infinitely many pairs of primes with a bounded gap. The gap might not be exactly 2, but it's finite. There are infinitely many prime pairs separated by, at most, some fixed number. This was a major breakthrough, even though it doesn't quite prove the twin prime conjecture. The twin prime conjecture is part of a larger pattern of questions about the distribution of primes. How close together can primes be? How far apart can they be? Are there patterns in the gaps between primes? These questions are central to number theory. Let's talk about something called Fermat's last theorem. This is one of the most famous theorems in mathematics, partly because it took over 300 years to prove. Fermat's last theorem says that there are no whole number solutions to a certain equation. The equation says one number to some power plus another number to that same power equals a third number to that power. For power 2, this works. Those are Pythagorean triples, but for any power greater than 2, there are no solutions in whole numbers. Fermat claimed to have a proof, but said the margin of his book was too small to contain it. For centuries, mathematicians tried to prove it. Many made progress on special cases, but the general theorem remained elusive. Finally, in the 1990s, Andrew Wiles proved it. His proof was over 100 pages long and used incredibly advanced mathematics, far beyond anything Fermat could have known. It's almost certain that Fermat didn't actually have a proof. He probably made a mistake, thinking he had one when he didn't. But the quest to prove Fermat's last theorem drove huge advances in number theory. Techniques developed to attack the problem turned out to be useful for other questions. The theorem itself isn't particularly useful, but the mathematics created along the way was invaluable. This is a common pattern in mathematics. A seemingly simple question leads to deep investigations, and the journey is more important than the destination. Fermat's last theorem exemplifies this perfectly. Let me tell you about something called the Euler characteristic. We mentioned Euler's formula for polyhedra earlier. The Euler characteristic is a generalization of that idea. For any polyhedron, you can compute a number by counting vertices, subtracting edges, and adding faces. For a sphere or any shape topologically equivalent to a sphere, you always get 2. For a torus, you get 0. For a surface with more holes, you get a negative number. This number, the Euler characteristic, is a topological invariant. It doesn't change when you deform the shape. You can stretch, twist, or bend the surface, and the Euler characteristic stays the same. It's a property of the topology, not the geometry. The Euler characteristic connects to all sorts of other areas. In algebraic topology, it's related to homology groups. In differential geometry, it's related to curvature. There's the Gauss-Bonnet theorem, which says that if you integrate the curvature over a surface, you get a multiple of the Euler characteristic. This is a deep connection between local geometric properties and global topological properties. The Euler characteristic also appears in graph theory. For a connected planar graph, if you count vertices minus edges plus faces, you get 2. This is because a planar graph divides the plane into regions, and the graph together with these regions has the topology of a sphere. These connections show how different areas of mathematics interweave. A simple counting formula for polyhedra turns out to be related to curvature, homology, and graph structure. Mathematics is deeply unified, with threads connecting disparate topics. Alright, let's think about something called the hairy-ball theorem again, but consider its implications more broadly. The theorem says you can't comb a sphere flat. There must be a point where the combing fails, where you have a discontinuity or a zero. This has implications beyond just combing hair. Any continuous vector field on a sphere must have a zero somewhere. In physics, this applies to things like magnetic fields, wind patterns, and more. The Earth's atmosphere is a vector field on a sphere. The Hairy-Ball theorem guarantees there's always a point of zero wind, like the center of a high-pressure system or a calm spot. There's a generalization to higher dimensions. In even dimensions, you can't have a non-zero continuous vector field on the sphere. But in odd dimensions, you can. The circle, which is a one-dimensional sphere, can have a non-zero tangent vector field everywhere. Just pick a direction and go around. The three-dimensional sphere, living in four-dimensional space, also allows non-zero vector fields everywhere. This pattern, alternating between even and odd dimensions, is related to the structure of normed division algebras. There are only four of them: real numbers, complex numbers, quaternions, and octonions, and their dimensions are 1, 2, 4, and 8. These are precisely the dimensions where you can have certain kinds of nice multiplication structures. The Hairy-Ball theorem is part of a larger tapestry of results in topology about what kinds of structures can exist on spheres of different dimensions. It's a rich area with surprising connections to algebra and geometry. Let's talk about P-adic numbers again, but think about them geometrically. We said P-adic numbers measure size differently. Numbers with many factors of a prime are considered small. This seems backwards, but it's self-consistent. In P-adic geometry, points that are close in the usual sense can be far apart in the P-adic sense, and vice versa. The P-adic topology is completely different from the usual Euclidean topology. Sets that are open in one topology might be closed in the other. Despite this weirdness, P-adic numbers obey all the same algebraic rules as real numbers. You can add, subtract, multiply, and divide. You can take limits and do calculus. It's a complete number system, just like the reals, but the geometry is alien. P-adic numbers are useful in number theory because they give a different perspective on problems. Sometimes a problem that's hard over the real numbers becomes easier over the P-adics. Or sometimes you can solve a problem over the reals and over all the P-adics separately and combine the solutions to get information about the original problem over the integers. This is called the local global principle. To understand something about whole numbers, you study it locally, meaning modulo primes or using P-adics, and globally, meaning over the reals. Then you try to piece together the local and global information. This strategy has been incredibly fruitful in number theory. Let me tell you about the Goldbach conjecture again, but with more context. The conjecture says every even number greater than 2 is the sum of 2 primes. Like 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 3 plus 7, or 5 plus 5. Computers have checked this for enormous numbers, trillions and trillions. Every even number tested is indeed the sum of 2 primes, but there's no proof it works for all even numbers. There could be some gigantic even number somewhere that can't be written as the sum of 2 primes. We just don't know. There have been partial results. Chen's theorem, proved in the 1970s, says every large enough even number is the sum of a prime and a number that's either prime or the product of 2 primes. This is close to the Goldbach conjecture, but not quite the same. It shows that even numbers can be written as sums in ways very close to what Goldbach conjectured. There's also a weaker version called the weak Goldbach conjecture, or the odd Goldbach conjecture. It says every odd number greater than 5 is the sum of 3 primes. This was proved in the 21st century. So we know the weak version is true. But the strong version, about sums of 2 primes, remains open. The Goldbach conjecture is emblematic of problems in number theory. Simple to state, easy to verify for small cases, but apparently fiendishly difficult to prove in general. It's likely that proving it will require entirely new techniques or insights we don't have yet. Let's think about calculus for a moment, but not the mechanics of taking derivatives or integrals. Think about what calculus is really doing. Calculus is the mathematics of change. It lets you analyze how things vary, how rates of change themselves change, how quantities accumulate over time. Before calculus, mathematics was largely static. Geometry dealt with fixed shapes. Algebra dealt with static equations. Calculus introduced dynamics. It let you model motion, growth, decay, optimization, anything that changes. The two main operations in calculus, differentiation and integration, are inverses of each other. Differentiation tells you the rate of change. Integration accumulates changes to find the total. The fundamental theorem of calculus says these operations undo each other, linking them in a profound way. This connection was revolutionary. Newton and Leibniz, who independently invented calculus, both recognized this fundamental link. It unified what had been disparate techniques for finding areas, tangents, and rates of change. It showed they were all part of a single coherent framework. Calculus is the foundation of physics. Newtonian mechanics is formulated in terms of derivatives. Maxwell's equations for electromagnetism are differential equations. Einstein's general relativity uses advanced calculus in curved spaces. All of modern science relies on calculus to describe how the world works. And calculus is continuously evolving. There are generalizations to infinite dimensions, to abstract spaces, to settings where the traditional assumptions don't apply. Functional analysis, differential geometry, stochastic calculus all extend the ideas of calculus in new directions. Let me tell you about the Collatz conjecture again, but think about why it's so hard. The problem is that the rule involves both multiplication and division. When the number is odd, you multiply and add. When it's even, you divide. These operations interact in complicated ways. Multiplication tends to make numbers grow. Division tends to make them shrink, but they don't balance neatly. Depending on the sequence of odd and even numbers you encounter, you can have runs of growth or runs of shrinkage. The trajectory is erratic. What makes the Collatz conjecture tantalizing is that despite the erratic trajectories, all tested numbers eventually reach one. There seems to be an attractor. No matter where you start, you're pulled toward the same endpoint. But we can't prove this happens for all numbers. One approach to the conjecture is statistical. If you think of the rule as approximately halving the number on average, then numbers should tend downward. On average, you'd expect to reach one. And this statistical argument matches what we observe. But mathematics requires certainty, not just probable outcomes. So the statistical argument doesn't constitute a proof. Another approach is to look for patterns or invariants. Maybe there's some property that's preserved or changes predictably under the Collatz rule. If you could find such a property, you might be able to prove all numbers eventually reach one. But so far, no one has found the right invariant. The Collatz conjecture might be genuinely hard, requiring new mathematical techniques, or it might have a clever, simple proof that we're missing. Either way, it remains one of the most frustrating unsolved problems in mathematics. Alright, I think we've covered a lot of ground tonight. We've explored infinity, zero, imaginary numbers, paradoxes, primes, fractals, topology, probability, chaos, and so much more. These ideas all show the richness and depth of mathematics. Mathematics isn't just calculation, it's a way of thinking, a way of exploring patterns and structures. It's creative and intuitive, as much an art as a science. The ideas we've discussed tonight have fascinated people for centuries and will continue to fascinate people for centuries to come. Whether you're falling asleep now or still wide awake, I hope this journey through mathematics has been interesting. There's always more to discover, always deeper questions to explore. Mathematics is an endless landscape of ideas, and every generation adds to our understanding. Thanks for listening. Rest well, and maybe you'll dream of infinity.